The Earth is not as alone in space as once believed. Though it may sound like a peculiar notion for a topic rooted in astronomy, a long-standing whisper among scientists suggests that elusive companions may be trailing the planet, enigmatic formations drifting silently in orbital harmony. These spectral entities, barely perceptible and shrouded in ambiguity, are said to reside in a delicate gravitational dance with Earth, suspended at the cosmic crossroads known as the Lagrange points. Some observers claim to have glimpsed these ethereal structures, vast, dim patches of particulate matter, stretching many times the width of Earth. Yet repeated attempts to confirm their presence have often yielded only empty skies, leaving the astronomical community in a state of unresolved curiosity for over 60 years. Are these strange apparitions mere tricks of light and shadow, or do they point to a deeper, hidden complexity in Earth's celestial environment? What kind of phenomenon could be simultaneously so immense and so elusive? Is the Moon truly Earth's only partner on its solar voyage? At the heart of this mystery lies the concept of ghost moons, a controversial and captivating subject that continues to intrigue scientists and enthusiasts alike. The story begins in 1961, when Polish astronomer Kazimierz Kordylewski reported observing faint cloud-like formations in regions of the sky corresponding to the L4 and L5 Lagrange points of the Earth-Moon system. These locations, forming equilateral triangles with Earth and its satellite, are known for their gravitational stability, a delicate balance where the forces acting on a smaller object counterbalance its orbital motion, allowing it to remain stationary relative to the two larger bodies. Named after the 18th century mathematician Joseph Louis Lagrange, who first theorized their existence, Lagrange points are not unique to the Earth-Moon system. They appear in all two-body gravitational systems, such as Earth and the Sun or Jupiter and the Sun, and are designated as L1 through L5. Among these, L1, L2 and L3 are unstable, requiring constant adjustments for objects to remain in place, as exemplified by satellites like SOHO and the James Webb Space Telescope. These points represent precarious positions where even minor disturbances like solar radiation or gravitational tugs can displace objects from their orbits. In contrast, L4 and L5 are bastions of stability. These regions can trap matter, such as dust or asteroids, allowing it to co-orbit with Earth without the need for continuous correction. It was in these stable pockets of space that Kordylewski believed he had found diffuse cloud-like dust formations, later referred to as the Kordylewski dust clouds. His announcement stirred excitement and skepticism alike. Despite Kordylewski's initial findings, attempts to observe the clouds in subsequent years largely ended in failure. Limitations in observational technology at the time hindered efforts to confirm the discovery. Many scientists speculated whether the supposed clouds were real structures or optical artifacts caused by scattered light and atmospheric distortion. The debate has persisted for decades, feeding both scientific inquiry and imaginative speculation. Even now, with modern instruments and renewed interest, the question remains tantalizingly open. Do these ghostly clouds truly exist, silently sharing Earth's path around the Sun? Or are they merely a mirage conjured by gravitational coincidence? Detecting extremely faint structures amid the vast darkness of space has always posed a formidable challenge. This difficulty bred a scientific skepticism that endured for decades. Occasionally, astronomers reported fleeting glimpses of elusive dust clouds located near the Earth-Moon system's Lagrange points, particularly L4 and L5. At times, these clouds were seen in both regions simultaneously. A handful of researchers, including Kazimierz Kordylewski, the cloud's namesake, succeeded in photographing them. However, the resulting images were so dim that they could not be reproduced in popular media, such as newspapers. These were not photographs in the conventional sense. Capturing the ethereal presence of these clouds required photometric imaging, which, honestly, is quite an exacting process involving glass photographic plates and extended exposure times to register even the dimmest celestial illumination. Unlike the crisp, detailed images we get from instruments like the Hubble Space Telescope, these photos were primarily used to detect subtle fluctuations in light intensity. These changes served as indirect evidence of the cloud's existence. In 1966, NASA took a significant step forward by launching an airborne observational campaign from its Convair 1990 jet laboratory, flying above 12,000 meters, to escape the interference of terrestrial light pollution. Over the course of 4 flights, scientists aboard the aircraft confirmed the presence of Kordylewski dust clouds at both L4 and L5. Remarkably, they even succeeded in photographing the cloud at L5. That same year, the orbiting Solar Observatory OS-06 also recorded data supporting the cloud's presence and contributed to the initial efforts in quantifying their brightness and spatial extent. Yet, this growing body of observational data was soon met with theoretical resistance. In 1976, Siegfried Rosa, an astronomer at the Max Planck Institute for Astronomy, employed numerical simulations to demonstrate that dust accumulation at L4 would be dynamically unstable. He proposed that solar radiation, the solar wind, and gravitational disturbances from planetary bodies rendered the region inhospitable for persistent dust concentrations. Around this time, radar observations also failed to detect any significant structures, casting further doubt on the cloud's existence. The skepticism deepened in 1983 when a team operating a 61-centimeter telescope near Tucson, Arizona, found no trace of the dust clouds in either Lagrange point. However, the story was far from over. In 1989, astronomer Maciej Winiarski reignited interest in the phenomenon with new photographic evidence obtained from an observatory in Poland's Bieszczady Mountains. These observations indicated that the KDCs spanned several degrees in apparent diameter. Most notably, Winiarski's work marked the first time the clouds were observed using 3-color photometry. The results revealed that the dust exhibited a distinctly red hue, significantly redder than the typical counterglow produced by sunlight scattered off interplanetary dust. This chromatic anomaly implied a compositional difference, raising a compelling question. What is the origin of this unique material? But just as momentum was building again, another blow to the hypothesis arrived in 1991. Japan's Heightened spacecraft conducted a single pass through the L4 and L5 regions in a search for dust particles, but came up empty. Still, astronomers cautioned against drawing definitive conclusions from this mission. The probe completed only one loop around each point, and if the KDCs do exist, their constituent dust may have been moving too slowly to register on Heighten's detectors. Thus, the debate that began in 1961 with Kordylewski's initial claims has endured, shaped by a fluctuating interplay of observation, skepticism, and renewed interest. Across decades of inquiry, the existence of these mysterious clouds remains, well, an open question, teetering on the edge of belief and disbelief and inviting further exploration into one of space's more elusive phenomena. In recent years, scientists have achieved a significant milestone in understanding the elusive nature of the Lagrange point 5 Kordylewski dust clouds, or L5 KDCs. Back in 2018 and 2019, astronomer Judith Slisba-Log, along with physicists Gabor Horvath and Andras Barta, provided compelling observational evidence of these dust clouds by analyzing how they scatter polarized light. By employing a technique known as polarized imaging, they use specialized filters capable of detecting light reflected at specific angles, which honestly revealed subtle patterns invisible to the naked eye. As light interacts with dust particles, it scatters in ways that depend on the composition and spatial arrangement of the particles. The research team captured a sequence of images using different polarized filters and discovered that the light patterns observed closely aligned with theoretical models predicting the behavior of sunlight scattered by particulate clouds. These observations led them to conclude that the scattering phenomena observed could only be attributed to dust particles. To reinforce their findings, the team conducted advanced computer simulations that modeled the dynamics of approximately 1.86 million dust particles in the vicinity of the L5 point. These simulations demonstrated that, under suitable gravitational and orbital conditions, dust could become gravitationally trapped at L5 and persist for extended periods. The resulting virtual dust clouds closely resembled the actual structures captured in the polarized images, with fine particles dispersed over an expansive region. However, a question has lingered in the scientific community. Why have some astronomers succeeded in detecting and photographing these clouds, while others have reported no evidence of their existence? The answer may lie in the ephemeral and diffuse nature of the KDCs themselves. Despite spanning an enormous area, roughly 100,000 by 70,000 kilometers, nearly 9 times the diameter of Earth, the total mass of these clouds is astonishingly low. The dust particles that comprise them are extremely small, often just a few microns or even submicron in size, comparable to the dimensions of bacterial cells. A micron is 1/1,000,000th of a meter, meaning individual particles are invisible without the aid of high-powered microscopy. Further complicating detection is the structure of the KDCs. According to models presented by Slisbalog and Horvath in 2018, the cloud at L5 does not form a static, uniform entity. Instead, it exhibits a fluctuating distribution, with particle density varying both spatially and temporally in response to the Moon's orbit. This suggests that the KDCs are not stable, permanent formations, but rather transient and dynamic, more akin to an atmospheric dust storm than a fixed object in space. Such volatility makes these clouds particularly difficult to observe. Forces such as solar wind and gravitational perturbations from the Sun or, nearby planets can disrupt the delicate balance that sustains them, causing them to dissipate and then slowly reassemble. This constant cycle of formation, dispersion and reformation, combined with the minuscule size of the particles and their diffuse spread, offers a compelling explanation for why the L5 KDCs have, evaded consistent detection over the past 30 years. In 2018, the tentative confirmation of the Kordylewski dust cloud near the Earth-Moon L5 Lagrange point reignited scientific interest, though it did not resolve the ongoing debate about the cloud's permanence. Researchers remain divided on whether these dust accumulations are stable, long-standing phenomena or transient structures influenced by gravitational forces from the Sun and neighboring planets. What is no longer in question, however, is their reality. These are not optical illusions or observational errors, they are genuine components of the Earth-Moon system. Although the detailed characteristics of KDCs, their internal composition, their formation dynamics, and their evolutionary timeline remain under scrutiny, the scientific consensus increasingly supports their legitimacy and significance. Often described as ghost moons due to their faint appearance and ephemeral presence, they differ markedly from the more familiar mini-moons and quasi-moons that have occasionally joined Earth's orbit. Mini-moons, for example, are typically small rocky bodies that enter Earth's gravitational grasp for brief periods, usually less than a year, before continuing their journey through the solar system. Unlike the transient nature of these solid objects, the Lagrange points where KDCs gather have been gravitationally stable since the Earth-Moon system formed, possibly making these dust clouds ancient in origin. A key distinction lies in physical structure. While mini-moons and quasi-moons are solid bodies, KDCs are diffuse, ever-shifting clouds composed of countless fine dust particles. Quasi-moons appear to orbit Earth from certain observational angles, yet they are in fact solar orbiting asteroids that occasionally loop near our planet. Meanwhile, mini-moons are genuine Earth satellites, albeit tiny and elusive. Only 4 have ever been definitively recorded. One example is 2020 CD3, a small object temporarily captured by Earth's gravity between early 2019 and mid-2020, acting as a brief secondary moon. Among these obscure moon-like companions, KDCs stand out due to their mysterious, almost spectral nature. Despite being diffuse and dynamic, they persist in a semi-stable configuration, hinting at a long-term role in the Earth-Moon environment. The effort to observe them has pushed the boundaries of astronomical techniques, often operating at the very limits of visibility. As observational tools and detection methods continue to evolve, so too does the potential for a deeper understanding of these enigmatic structures. Future studies are poised to focus more intently on the L4 region, which has historically received less attention than its L5 counterpart. Renewed radar surveys and advanced imaging methods may uncover previously missed features, challenging past null results and strengthening the case for these elusive clouds. With growing acceptance within the scientific community, researchers can now turn toward fundamental questions. How are KDCs replenished? What role might they play in space weather or satellite dynamics? Do they influence the broader near-Earth environment? Whether they are permanent fixtures or intermittent visitors sculpted by celestial forces, Kordylewski dust clouds serve as a compelling reminder that our cosmic backyard still holds many secrets. Their ghostly presence across the night sky speaks not of fantasy, but of an unexplored reality, one that invites deeper inquiry and promises new discoveries in the shadows of our own planetary system. If you found this journey into cosmic dust and hidden moons fascinating, don't forget to like the video, share it with fellow space enthusiasts, and subscribe to the channel for more explorations into the wonders of our universe. Your support helps fuel the curiosity that keeps these discoveries alive. Until next time, keep looking up.